Hello and welcome back to another video from CHE 101. I am Cassandra Santa Ana from the Academics Committee of the Chemical Engineering Society. And in this video, I will be discussing how to solve nth-order homogeneous linear ODEs under differential equations or Cal-Eng 3. For this video, I am first going to provide a short introduction wherein we define an nth-order homogeneous linear ODE. Then I will discuss the general procedure for solving. This includes four main parts: real and distinct roots, real and repeated roots, imaginary and distinct roots, imaginary and repeated roots. After which I will be presenting four sample problems, and then I will be walking you through the solutions of each one. And lastly, we'll have a short recap of the entire discussion. So first, let us define an nth-order homogeneous linear ODE. A linear ODE is a differential equation in which the dependent variable, in this case y, and its derivatives, so that's dy over dx, all occur to only the first degree. This means that they are not raised to powers greater than 1, and they also cannot be present in products. Then here in this equation, a sub 0, a sub 1, and so on and so forth, those are the constant coefficients of the linear ODE. So the r of x of the equation, which we can see here as the right-hand side, tells us whether it is homogeneous or not. If r of x is equal to 0, it is homogeneous, and if it is not equal to 0, it is non-homogeneous. Alright, so for the general procedure of solving nth-order homogeneous linear ODEs, the first step is to rewrite the original differential equation in terms of the differential operator, which is represented by a capital D. Now, this is pretty straightforward. So first-order derivatives are represented by d raised to 1, or just d. Second-order derivatives are represented by d raised to 2, so on and so forth. And as you can notice here, we usually factor out the y, or the dependent variable, because it is present in all terms anyway. The reason why we did that first step is to make it easier for us to do this second step, which is to form the auxiliary equation. Basically, you take the ODE expressed in the differential operator and replace the capital D with the letter M. Also, you can remove the y, or the dependent variable, when writing the auxiliary equation. Now, your auxiliary equation basically looks like a polynomial function in terms of m. Next, we solve for the roots of the auxiliary equation. So there are four types of possible roots that you may solve for. M may either be real and distinct, real and repeated, imaginary and distinct, or imaginary and repeated. Real and distinct roots will take on this form of the general solution. C is an arbitrary constant, while m are the roots of the auxiliary equation. So y equals c sub 1 times e raised to m sub 1x plus c sub 2 times e raised to m sub 2x, and so on and so forth. Now for real and repeated roots, this is the form of the general solution. M is the repeated root, and n is the number of times that root was repeated. So y is equal to the quantity c sub 1 plus c sub 2x plus c sub 3x squared, so on, times e raised to mx. Now for imaginary roots, they will always take on the form a plus or minus bi, where a and b are constants. If you have distinct imaginary roots, they should take on this form of the general solution. So y is equal to the quantity c sub 1 sine bx plus c sub 2 cosine bx times e raised to ax. And lastly, for imaginary and repeated roots, they will take on this form of the general solution. So y is equal to the quantity c sub 1 plus c sub 2x, plus c sub 3x squared, so on, times cosine bx, plus c sub 2 cosine bx, times e raised to ax. And lastly, for imaginary and repeated roots, they will take on this form of the general solution. So y is equal to the quantity c sub 1 plus c sub 2x, plus c sub 3x squared, so on, times cosine bx, plus the quantity c sub n plus 1 plus c sub n plus 2x plus c sub n plus 3x squared, so on, times sine bx, all multiplied to e raised to ax. Now at this point, we've already discussed all the necessary formulas. So let me show you some sample problems so that you can understand our lesson better. So for our first problem, we have the second derivative of y with respect to x plus 4 times dy over dx minus 21y equals 0. So first, we rewrite the original ODE in terms of the differential operator. So that is the quantity d squared plus 4d minus 21 times y equals 0. Next, we use that equation so that we can easily form the auxiliary equation. So that's going to become m squared plus 4m minus 21 equals 0. Lastly, we get the roots of the auxiliary equation. So what I did is I factor out the auxiliary equation. So we get the quantity m plus 7 times the quantity m minus 3 equals 0. From this, we can determine that our roots are negative 7 and positive 3. From this, we can say that the roots of our auxiliary equation are real and distinct. Therefore, it will take on this form of the general solution. We will substitute these roots in the place of m. So our final answer for the general solution of this equation is y equals c sub 1 times e raised to negative 7x plus c sub 2 times e raised to 3x. Okay, so for problem number 2, we have y triple prime minus 5y double prime plus 3y prime plus 9y equals 0. So again, we rewrite the original ODE in terms of the differential operator. So we get the quantity d cubed minus 5d squared plus 3d plus 9 times y equals 0. Then from there, we can form the auxiliary equation. So we will get m cubed minus 5m squared plus 3m plus 9 equals 0. We then have to get the roots of the auxiliary equation. So what I did is that I used synthetic division to divide the expression by m plus 1, which turns out to be one of its factors. I then end up with the quantity m plus 1 times the quantity m squared minus 6m plus 9 equals 0, which can then be further simplified to the quantity m plus 1 times the quantity m minus 3 squared equals 0. From this, we can then determine our roots, which are negative 1, 3, and 3. Now, our roots are all real numbers, but 3 is repeated twice. Hence, for those repeated roots, their general solution will take on this form. So, plugging in the values of our roots, the general solution for the given differential equation will then be y equals c sub 1 times e raised to negative x plus the quantity c sub 2 plus c sub 3x times e raised to 3x. Okay, so for problem 3, this is already written in terms of the differential operator. So we have the quantity d cubed minus 5d squared plus 24d minus 20 times y equals 0. Now we can go straight to forming the auxiliary equation. So we have m cubed minus 5m squared plus 24m minus 20 equals 0. Then we get the roots of this equation. So again, I used synthetic division to divide the whole equation by m minus 1, which turns out to be one of the roots. We then end up with the quantity m minus 1 times the quantity m squared minus 4m plus 20 equals 0. I then equated each of these factors to 0. So equating m minus 1 to 0, we find out that one of our roots is 1. Now for m squared minus 4m plus 20, it's not as easy to determine the roots associated with this factor. So I transpose the constant 20 to the other side of the equation, and then I performed completing the square by adding 4 to both sides of the equation. So this gives us the quantity m minus 2 squared equals negative 16. And then isolating m on one side of the equation, we get m equals 2 plus or minus 4i as our other roots. So we can see here that we have one real root and two distinct imaginary roots. So the imaginary roots will then take on this form of the general solution. Our final answer will then be y is equal to c sub 1 times e raised to x plus the quantity c sub 2 times sine 4x plus c sub 3 times cosine 4x multiplied to e raised to 2x. And then for our last problem, we have the fourth derivative of y with respect to x plus 18 times the second derivative of y with respect to x plus 81y equals 0. So again, we rewrite the given differential equation in terms of d. This gives us d raised to 4 plus 18d squared plus 81 times y equals 0. We then form the auxiliary equation, m raised to 4 plus 18m squared plus 81 equals 0. Then after this, we have to get the roots of the auxiliary equation, which is plus or minus 3i and plus or minus 3i. So I think one tip when solving for the roots, look at the highest order derivative. So in here, in this example, we have a fourth order derivative as the highest. That means the auxiliary equation should have 4 roots. So that's true for what we solved. Plus or minus 3i counts as 2 roots, and the other plus or minus 3i counts as 2 roots as well. Our roots for this problem are imaginary and repeated, so they have to take on this form of the general solution. So our final answer will then be the quantity c sub 1 plus c sub 2x times cosine 3x plus the quantity c sub 3 plus c sub 4x times sine 3x. So that is our last problem for this video tutorial. Alright, so for a short summary of the entire discussion, let's go back to the definition. So an nth order homogeneous linear ODE takes the form shown on the screen, where r of x, or the right-hand side, must be equal to 0. And next, the general procedure for solving nth order homogeneous linear ODEs is as follows. First, you have to rewrite the original differential equation in terms of the differential operator. Next, you have to form the auxiliary equation in terms of m. Third, get the roots of the auxiliary equation. And fourth, obtain the general solution based on the type of roots of the auxiliary equation. That will be all for this video. So if you have any further questions, you can contact the Chen Academics team through email or through the Facebook link flashed on the screen. Well, I really hope that you learned something new from us today. Thank you for watching and stay tuned for more CHE 101 tutorials.